The deep winter air bites. It is a physical assault, a cold that bleeds the heat from bone and muscle, dropping temperatures across the Great Lakes region and the eastern woodlands to fatal levels. For months, the land lies locked beneath ice. Resources are scarce, and the constant crushing wind drives every living creature toward desperation. To survive here, not just for a few days, but for the entire long season, demanded more than simple fortitude. It demanded genius. Imagine the wind roaring through the skeletal branches of the hardwood forest, carrying sharp pellets of snow. Outside, the world is pure hazard. Inside, there must be sanctuary. The challenge facing the ancestral peoples of this region, the Haudenosaunee, the Wendat, and others, was not merely how to build a shelter, but how to engineer a massive, resilient vessel capable of sustaining dozens, sometimes hundreds, of human lives through relentless environmental punishment. Their solution, born from deep ecological understanding and sophisticated architectural geometry, was the Longhouse. It was the ultimate machine for collective survival, built entirely from the forest itself. This was not a temporary camp or a flimsy hut. The Longhouse was an engineered structure, often exceeding 200 feet in length, 50 feet in height, and 30 feet wide. It was a communal citadel designed specifically to manage thermal load, shed massive snowfalls, resist hurricane-force winds, and facilitate the complex social and political life of an entire clan. Its construction reveals an intricate understanding of material science, civil engineering, and applied physics, all achieved without iron, nails, or modern power tools. The structure itself embodied the fundamental principles of adaptation: resilience through flexibility, warmth through mass, and survival through collaboration. To understand the Longhouse, we must first understand the environment it was designed to defeat. The winters in the territory occupied by the Iroquoian peoples, stretching from present-day upstate New York, across southern Ontario, and parts of Pennsylvania, are characterized by extreme variability, profound cold spells, and massive snow loads. The annual freeze-thaw cycles also pose a significant challenge to any permanent structure, threatening the foundation with frost heave and destabilization. The initial active engineering centered on location and orientation. A Longhouse village was typically situated on high ground, often near a defensible ravine or river, providing good drainage and tactical advantage. Crucially, the long axis of the structure was almost always oriented away from the prevailing winter winds. In much of the Northeast, this meant a strategic alignment, often running roughly northeast-southwest or parallel to the ridgelines, allowing the shorter, more heavily reinforced end walls to bear the brunt of the weather. This simple directional choice drastically reduced wind pressure on the broad sidewalls, minimizing heat loss through convection. The second critical phase was establishing the foundation. Stability was paramount. Unlike many modern structures anchored by deep concrete footers, the Longhouse utilized a system of deep, packed earth post holes or continuous trenches. Massive, carefully selected upright posts, the structural piers, were set deep into the ground, sometimes 4 to 6 feet down, passing below the typical frost line. This depth anchored the structure against the powerful uplift forces generated by high winds and prevented the seasonal expansion and contraction of frozen soil from pushing the posts out of alignment. These main vertical supports, often sturdy cedar or white pine logs roughly a foot in diameter, formed the skeletal spine of the building. Spaced gaps 10 to 12 feet apart, they defined the communal aisles and the central walkway. These primary posts were then reinforced by a grid of smaller, flexible saplings bent inward to create the distinctive barrel-vaulted roof profile. This use of primary, load-bearing posts, coupled with secondary, flexible supports, is a hallmark of engineered resilience. The selection of wood was a precise science based on function. For the primary, load-bearing uprights, species like eastern white cedar or hemlock were favored for their resistance to decay when buried in the soil and their straight-grained strength. For the vast network of rafters and purlins, the structural ribs of the roof, Lighter, highly pliable woods like ash or hickory were preferred. These thinner poles, usually 3 to 5 inches in diameter, needed to flex under snow load and wind shear without snapping, distributing the stress across the entire frame. The process of felling and shaping these timbers without metal implements was an exercise in systematic efficiency. Large trees were often ringed and felled using controlled burning at the base, followed by tedious scraping and chopping with stone axes or hardened shell adzes. Once felled, shaping was done primarily through charring and scraping, a method that not only shaped the wood but also hardened the surfaces, providing a degree of pest resistance. Perhaps the most ingenious aspect of the Longhouse frame was the connection system. Lacking nails, every joint, every intersection of post and beam was secured using natural cordage. The primary material was often stripped bark from basswood or slippery elm, materials that are incredibly durable when twisted into rope, resistant to weathering, and, crucially, elastic. This elasticity is the hidden engineering secret of the Longhouse. A rigid, nailed structure tends to fail catastrophically when subjected to extreme external forces like gale force winds. The Longhouse, however, was designed to sway. The thousands of flexible lashings, taut knots, often using a specialized square lashing pattern, allowed the entire structure to absorb tremendous kinetic energy. Instead of fracturing, the framework yielded slightly, dissipating the stress, and then returning to its original position. It was a living, breathing architectural system, deeply connected to the natural dynamics of the wind and the earth. Once the massive skeleton was complete, a process that involved the coordinated effort of the entire clan, the structure had to be enclosed. This enclosure was the difference between life and death, serving as the insulation layer that held the manufactured warmth inside. The material of choice for the walls and roof was bark, typically sourced from the mighty elm tree, though cedar or sometimes spruce bark were also used, depending on regional availability. Elm bark was highly prized for its thickness, pliability, and its natural resistance to water penetration. Harvesting bark was a seasonal operation, performed only during the spring and early summer when the sap was running strongly. This time allowed the thick outer layers to be carefully peeled away from the cambium layer in large cohesive sheets, often 3 to 4 feet wide and 6 to 10 feet long. The sustainability of this practice necessitated careful management of the surrounding forest, reinforcing the Longhouse people's deep reliance on and respect for their environment. These sheets of bark were carefully flattened and dried, sometimes weighted down with stones to prevent curling. They were then systematically layered onto the latticework of the frame, applied like massive overlapping shingles. Starting at the bottom, each sheet overlapped the one below it, directing rainwater and melting snow downward and outward. This method of shingling, centuries older than European roofing techniques, ensured waterproof integrity. Attachment of the bark sheath was meticulous. Small holes were punched through the bark, usually using a bone awl, and tied directly to the interior frame using more basswood cordage or strips of leather. External poles, battens, were often lashed over the bark sheets, running horizontally across the entire structure. These battens acted as reinforcing ribs, pressing the bark tightly against the underlying frame, securing the insulation layer against the constant threat of wind peeling, and ensuring the aerodynamic smoothness necessary for the roof to shed precipitation effectively. The roof, the greatest surface area exposed to the elements, utilized the distinctive semicircular or barrel vault profile. This shape served multiple engineering functions. First, it eliminated flat surfaces, preventing the accumulation of heavy snow loads that could crush the interior supports. Snow tends to slide efficiently off a curved profile. Second, the shape provided aerodynamic advantages, allowing strong winds to flow smoothly over the structure rather than creating high pressure points or turbulence that could rip the bark free. The insulation provided by the bark was augmented by the sheer thickness of the multiple layers and the internal air gaps. Findings indicate that in high-quality construction, the walls might comprise 2 to 3 layers of bark sheeting, potentially 6 inches thick when incorporating the underlying latticework and trapped air pockets. This created a formidable thermal barrier, slowing the transfer of heat from the inside to the freezing exterior. With the shell complete, the focus shifted to the interior physics of heat generation and retention. The Longhouse was, fundamentally, a heat battery, designed to capture and hold every source of thermal energy. The primary heat source was a series of central fire hearths, spaced regularly along the length of the dwelling, typically one fire pit for every 2 families, or about every 20-25 feet. These fires were critical not only for warmth, but also for cooking, curing hides, and providing psychological comfort. Maintaining multiple, small, continuous fires was significantly more thermally efficient than relying on 1 or 2 massive infernos, which would waste fuel and create uncontrolled heat spikes. The engineering challenge introduced by fire, however, is smoke management and air quality. If improperly managed, the structure would rapidly become uninhabitable due to smoke and, critically, the invisible killer, carbon monoxide. The solution was sophisticated ventilation, relying entirely on natural convection and the stack effect. Directly above each hearth, an opening, a smoke hole, was cut into the center ridge of the roof. These holes were relatively small and carefully designed. When a fire burned, the heated air became less dense and rose rapidly toward the ceiling. As this air rose, it pulled the combustion byproducts, smoke and carbon monoxide, with it, venting them outside. Crucially, this outflow had to be balanced by controlled inflow. The Longhouse was not hermetically sealed. Air needed to be drawn in from the outside to feed the fire's oxygen supply and replace the vented air. This replacement air was drawn in slowly and deliberately through the cracks and small intentional gaps at the base of the walls and near the doors. Because the fresh, cold air entered near the ground, it was immediately heated by the radiating warmth of the fires and the structure's thermal mass before circulating upward, minimizing uncomfortable cold drafts at the living level. To control the size and efficacy of the smoke hole, simple technological adjustments were employed. Evidence suggests the smoke holes were fitted with movable bark or hide dampers. Depending on the wind speed and direction, these dampers could be shifted slightly or completely closed to prevent rain, heavy snow, or fierce crosswinds from pushing smoke back down into the living space. This manual regulation of chimney draft was essential for maintaining a clear and healthy interior atmosphere. The interior architecture reinforced the thermal efficiency. The living spaces were organized laterally, in parallel to the central aisle where the fires burned. Along the side walls, raised sleeping platforms, bunks, were constructed. These platforms were built high enough off the dirt floor, often 18 to 36 inches, to serve a vital thermal purpose, separating the inhabitants from the cold ground, which acts as a powerful heat sink. These bunks were not merely beds, they were highly efficient heat traps. Often, 2 tiers were constructed, a lower level for sleeping and a higher storage rack suspended directly above. This upper rack served a dual purpose, storing food and tools, and, more importantly, capturing the rising warm air before it escaped through the smoke vents. This warm layer of air, trapped just beneath the roof, helped moderate the temperature for the upper sleeping tier, while providing a constant source of warm, dry air for curing meat, drying corn, and preserving important materials. The sleeping bunks themselves were further insulated using layers of woven mats, animal hides, and furs, creating localized, incredibly warm microclimates for the inhabitants. A longhouse could shelter 50 to 100 people. An adult human body generates substantial heat, roughly 100 watts at rest. In a well-insulated, massive structure, the collective body heat of 50 individuals provides a continuous, low-level thermal output equivalent to several small electric heaters, even if the central fires were allowed to burn down overnight. The architectural mass, the thick walls and packed earth floor, acted as a thermal flywheel, stabilizing the interior temperature against external fluctuations. The sheer scale of the Longhouse mandated a complex social structure to manage it. This was not a detached single-family home, it was a physical embodiment of the Haudenosaunee clan system. Each door and each fire hearth defined the social and political boundaries of the residence. The Longhouse typically housed an extended matriarchal lineage, Authority and resources were managed by the clan mother. The space was literally divided into compartments defined by the fires, separating the different family units. But the structure demanded constant cooperation. Fuel gathering, fire monitoring, structural maintenance, and food preparation were communal tasks. Failure to cooperate meant potential disaster for the entire group. Thus, the engineering solution was inextricably linked to the social engineering required to enforce harmony and shared responsibility. The construction phase itself was a massive logistical undertaking, requiring hundreds of human hours of concerted labor. Archaeological evidence suggests that the main frame of a substantial longhouse could be erected in a few weeks, but the detailed work of harvesting, processing, and lashing the bark sheathing could take months. This necessitated peak efficiency, often involving specialized labor divisions. Men typically handled the heavy timber felling and framing, while women were largely responsible for the critical, time-sensitive tasks of bark harvesting, preparation, and the detailed lashing of the frame and siding. The reliance on organic materials meant that the longhouse was not an eternal structure. Even the most decay-resistant cedar post, buried in moist earth and subjected to constant condensation, eventually succumbs to rot, insect infestation, or mold. Evidence suggests the structural lifespan of a longhouse was typically between 10 to 20 years. This inherent impermanence was deeply integrated into the cultural and environmental cycle of the people. They practiced swidden agriculture, shifting cultivation. After a decade or two, the soil surrounding the village would become depleted, and the readily available supply of large timber and bark within easy hauling distance would be exhausted. The dual necessities of replenishing resources and retiring the aging structure drove the cyclical migration of the entire village complex. The old structure was often dismantled or simply abandoned, allowing the materials to return to the earth, and a new village, a new generation of longhouses, would be erected in a fresh location. Beyond shelter, the longhouse was a fortified extension of the surrounding village defense. The villages were typically ringed by imposing palisades, tall walls constructed of closely set vertical logs sharpened at the top. These palisades provided a crucial layer of defense against rival groups and facilitated controlled access. The longhouse served as the ultimate refuge within this palisade. Its large, durable structure was vital for storing the winter's critical stores: dried corn, beans, squash, and cured meats. These supplies were stored high above the fires, protected from pests and the damp earth, leveraging the thermal environment for preservation. The security and mass of the longhouse ensured that the clan's vital supplies, the buffer between survival and starvation, remained intact throughout the hostile season. Let us delve deeper into the sophisticated materials handling required to manage the massive quantity of bark necessary for a large longhouse, which might require thousands of square feet of covering. The preference for elm bark was rooted in its unique cellular structure. Elm bark is thick, fibrous, and unlike many other tree species, retains its integrity when peeled and dried in large sheets. When cut across the grain, the fibers interlock, providing a material that is structurally robust yet lightweight enough to be handled and secured onto the frame. The preparation involved not only drying, but often a process of flattening under pressure and sometimes scoring the inner surface to prevent warping as moisture evaporated. The goal was dimensional stability, ensuring the sheets remained flat against the frame to minimize gaps that would invite drafts or water penetration. This preparation turned a natural material into a manufactured architectural component. In areas where elm was less available, cedar bark served as a robust, albeit heavier, alternative. Cedar contains natural oils, phenolics, that act as powerful preservatives, enhancing its water repellency and resistance to insect damage, a crucial attribute for a building designed to last over a decade. The trade-off was flexibility. Cedar is slightly more brittle than elm and required extremely careful handling during lashing. The thermal dynamics inside this massive volume were expertly managed using the principle of layered heat zones. While the fire aisle was the primary, high-temperature zone, the surrounding areas utilized passive heating strategies. The long, low mass of the structure meant that the sidewalls, especially in a dense village setting, were somewhat protected from the harshest winds. The massive frame and wall mass absorbed the heat radiated by the central fires throughout the day, releasing it slowly into the living quarters after the fires were banked at night. Even the materials used for the floor contributed to insulation.
The central aisle was often hard-packed earth, swept clean. However, the areas beneath the bunks and along the periphery of the house often featured layers of reeds, grasses, or pine needles. These organic materials provided a loose, insulating layer that trapped air, creating an additional buffer against ground cold, preventing the thermal bleed that plague modern uninsulated slab foundations.
Furthermore, the doors were engineered for minimal heat loss. At the narrow, heavily reinforced ends of the longhouse, the entrances were deliberately kept small. They were typically covered by heavy, layered curtains made of tanned hides or thick, framed bark shutters. In extreme cold, it is likely that a vestibule or double-door system, a small enclosed space that acted as an airlock, was used to ensure that when the outer door was opened, the warm interior air was not immediately sucked out by the external vacuum. This strategic entrance design showed a deep practical understanding of minimizing unnecessary air exchange. The efficiency of this ancient architecture can be measured against modern standards. While we rely on mechanical ventilation and forced air heating, the Longhouse utilized biomimicry and natural physics. Its curved roof mimicked the shape of an upturned boat or a large animal carapace, inherently aerodynamic and resistant to pressure. Its use of flexible joints mimicked the way natural materials survive storms, by yielding, not rigidity. The contrast between the interior and exterior environments was dramatic. During a typical January night, with external temperatures plummeting to -20 degrees Fahrenheit, evidence suggests the inner longhouse temperature, especially near the sleeping bunks, could be maintained in the comfortable range of 50 to 65 degrees Fahrenheit. This differential, a shift of 70 to 85 degrees, created entirely by wood, bark, and human management, is a colossal achievement in primitive environmental control. The role of smoke management extended beyond mere comfort. It was also a critical component of pest control and food preservation. The continuous low level of wood smoke that permeated the longhouse environment acted as a natural insecticide and bacteriostatic agent. Insects, rodents, and mold, all threats to stored food and structural integrity, were deterred by the smoky atmosphere. The materials used in construction, especially the basswood lashing and the bark sheeting, gained longevity from the constant exposure to smoke, which dried them out and infused them with preservative compounds. Let's consider the structural complexity of joining the roof elements. The barrel vault required massive rafters bent into shape.
This bending was likely achieved through a combination of controlled heat and moisture, steaming or soaking the saplings, and then anchoring them firmly under tension against the lateral purlins. Once secured, the natural tension of the wood created a robust, spring-like structure. If one point was stressed, the entire system absorbed and distributed the force, preventing localized failure. The ridge pole, running the length of the structure and connecting the apex of the rafters, was another masterpiece of joining technology. Since single timbers of this length were impossible to source, multiple poles were spliced together using overlapping joints, secured by hundreds of lashings. This splicing had to be strong enough to bear the dead load of the roof structure and the dynamic load of snow and wind, while maintaining perfect alignment for the smoke vents beneath. The social and psychological dimension of the longhouse cannot be overstated. Sharing such an intimate, large space for months of forced confinement demanded a high degree of social harmony. The architecture itself facilitated this. The central hearths were the nuclei of social life, offering light, heat, and activity. The peripheral bunks offered zones of semi-privacy, using mats and woven dividers to delineate family areas. This collective identity had spiritual dimensions as well. The structure was often conceptualized as a living entity, the back of a great tortoise, or a representation of the cosmos. The smoke rising through the central vents connected the mundane life of the dwelling with the spiritual realm above.
The building, therefore, was not merely protection, it was a profound symbol of order, unity, and the enduring connection between the people and the forested world that sustained them. In conclusion, the Longhouse represents a pinnacle of vernacular engineering, a powerful, integrated solution to a complex survival problem.
Its genius lies not in massive, rigid construction, but in elegant flexibility, smart material selection, and profound thermal management. The Haudenosaunee and other Iroquoian peoples created a technology entirely out of the landscape, capable of weathering the most violent seasons the North American continent could muster.
Modern archaeology relies heavily on the ghosts of these structures, the dark stains in the soil known as postmolds, to reconstruct the scale and precision of these ancient blueprints. These lines of post holes, stretching for hundreds of feet across former village sites, bear silent witness to the immense organizational capacity and architectural sophistication of the people who built them. They built a shelter that was durable enough to last 2 decades, yet gentle enough to yield to the wind, massive enough to house a clan, yet efficient enough to be warmed by basic fires and body heat. The Longhouse stands as an enduring testament to human ingenuity, a structure forged from wood, bark, and collective will, proving that the most sustainable, technologically advanced solution is often the one that works in deepest harmony with the environment it is designed to master. It was, and remains, a monumental achievement in survival architecture.